Wake up, because it's time to learn about quantum entanglement. Quantum entanglement is just one of the many strange properties of quantum mechanics, i.e. the study of the small. The quantum world is filled with many strange phenomena that, unlike classical physics, we can't actually visualize. For example, a particle doesn't exist in one specified state, but rather every possible state until it is measured. This means that we can't predict with absolute certainty where a particle is. Rather, we can only predict the probability of where it could be. This is called superposition. Quantum entanglement happens all the time by almost any form of physical interaction. To explain it, I'm going to use an example of an electron and its spin. When two electrons physically interact, they always have the opposite spin. Spin is a property of particles that, for the purposes of this explanation, we can naively envisage as an arrow. So what happens if we separate two entangled electrons over very large distances, placing them at each end of our galaxy, 100,000 light years away? When you measure the spin of the one, you know that the other will have the opposite spin. This means that the measurement of one is influencing the other instantaneously, whereas light would have taken 100,000 years to get there. So does this mean that information is traveling faster than light? Definitely not, because light is the universal speed limit. So in terms of our electron example, Einstein proposed an idea that at the moment of interaction, the electrons chose a specific spin. Therefore, when they moved far apart, they were already in that specific state. But most physicists didn't like this idea because it contradicts superposition. So they said that the electrons are in a fuzzy spin-up, spin-down state until they are measured. And instead, there's some strange quantum phenomenon happening, known as non-locality, or the ability for a particle to know another particle's state instantaneously. Thanks to an experiment by John Bell, physicists have been able to prove time and time again that Einstein's classical view was wrong, and the electrons in our example are indeed in a fuzzy spin-up, spin-down state until they are measured. But this doesn't mean that information can travel faster than light. Rather, it means our universe is non-local, a property Einstein was so desperately trying to save. Scientists have interpreted the results in different ways, but you can think of the two entangled particles as becoming part of the same quantum object. Therefore, from the moment of interaction, they are able to share information. I know this might sound strange to you, but remember, we can't actually visualize quantum phenomena. This is just one of the many examples that reminds us that in fundamental physics, things can get really weird. But thanks to maths and the physicists to interpret it, we can understand more and more with every theory, discovery, and experiment. I hope you enjoyed learning about quantum entanglement with me today.